Hello everyone, this is how I do the homework of section 1.3 property of matrix operation, page 38, question 25, 27, 33, and 35. For question 25, we have matrix A, B, and C. And the question has asked us to show AB matrix, the multiplication of matrix AB equals multiplication of matrix AC, yet B is not equal to C. So we can see to be two matrix equal B equals C, so each entry have to be the same. We can tell the entry is not so 1 is not equal to 7. So from by the first entry we can know B is not equal to C. And now we choose prove matrix A times matrix multiplied matrix B equals matrix A multiply matrix C. So let's do the calculation. So matrix A is -1, -2, 1, and 2 times matrix B is 1, 3, 2, -1. So we can have first row of like this times this vector. So we have -1 times -1 is -1, and plus -2 times 2 is -4. And this entry is going to be first row, second column. It is -1 times 3 is -3, plus -2 times -1 is 2. And second row, first column, 1 times 1, 2 times 2, and second row, second column, 1 times 3, 2 times -2, 2 times -1. Okay, we have -5, -1, 5, and 1. Alright, so that's from matrix A times matrix B. And now we do A times C, which is equals -1, -2, 1, and 2 times 7, 5, -1, -2. Alright, so we have -1 times 7, -7, plus 2, and -5 plus 4, 7, -2, 5, -4, which is equals -5, -1, 5, and 1. So we can see this is equals to this because each entry of the matrix is the same, and yet B is not equal to C. That's how we prove it. Okay, let's move on to question 27. So we have matrix A, which have three variable A, B, C, and then the second row, first column is 0. We need to find the all 2x2 matrix of the form matrix A that can satisfy A square equals identity matrix of 2x2. So let's find out what is the variable of matrix A, the square of matrix A. So A times A, which equals AB0C times AB0C, which we have now we have A square plus 0, which is this entry. And now we have AB plus BC. And now we have 0 plus 0. And at last we have 0 plus C square, which we need to be the result of identity matrix. So we can tell this doesn't conflict because 0 equals 0. And now, in order to be satisfied the identity matrix, we have to be A square plus 0 equals 1, right? So which is equals 1, and AB plus BC equals 0, and also C square equals 1. So each corresponding have the identity. So we need to solve this linear system. So we can know A square equals to 1. We have two answers, which we can be A equals 1 or A equals -1. And this one we can see either c equals 1 or c equals -1. So let's say if a equals 1 and c equals 1, in this case, let's satisfy those two, and we have to be ab plus bc equals 0, which is a is 1, that's b plus b equals 0. So we have, so b has to be 0. So we have first result of a equals 1, b equals 0, and c equals 1. And now we see if a equals 1, c equals -1, and now we have ab plus bc has to be 0, which is b, that's 1b, right? So plus c is -1, so -b equals to 0. So b can be any number. So b is any r, I assume. So that's for in case of a equals 1, c equals -1. In other case, it's a equals -1 and c equals to 1. And we have ab plus bc equals 0 and -b plus b equals 0. So we can get b, it can be any number. That's the other case. Let's see, we can find another case. If a equals -1 and c equals -1, we have ab plus bc equals 0. So that will be -b and -b equals 0. So -2b equals 0, and b has to be 0. So we have let's see another case. What if a equals -1 and c equals -1? So we need to satisfy this equals 0. So that will be -b minus b equals 0, -2b equals 0, which means b has to be 0 at this case. So in conclusion, we have 4 cases when a equals to 1, b equals and c equals to 1. In this case, we have b has to be 0. And also, the second case is a equals -1, c equals -1, and b has to be 0 as well. And the other two cases is the middle two. We have a equals -1, c equals 1, and b can be any number. And the last case, if a equals 1, c equals -1, and b can be any real number as well. So we can write down those in the form of matrix, 2 by 2 matrix, a, b, 0, c, right? So that's a is equals 1, c equals 1, b equals 0. That's the first case. Second case, that's -1, -1, and 0, and 0. And 3, which have -1, 1, and 0, can be a real number. That would be just a variable as well. And the last one, which is 1, 0, and -1, and b. So in any case, when we multiply together, that would be an identity matrix of 2 by 2. Okay, let's move on to question 33. We have matrix A as shown, and we need to find a to the 20 power, which it is a times a times a, and the total of a will be 20 of them. So what we can do is to see if we can find any patterns, since we can use parentheses to put them together. So if we try to find a pattern, so we might get an answer. So let's see, what if we just get 2 first? Let's get some space. 1, 0, 0, 0, -1, 0, 0, 0, 1. And that's the same. What we have is still the same, the basic calculation. 1, 0, 0, that would be 1. And this and this, that will be 1 times 0, 0 times -1, 0 times 0, that would be 0 as well. And the third, 1 times 0, 0 times 0, 0 times 1, that's 0 again. And let's see this one and this one. So 0 times 1, -1 times 0, 0 times 0, that will still be 0. And let's see second row, second column. 0 times 0 plus -1 times -1, that's 1. and 0 plus 0 times 0, that's still be 1. That will be 1. And let's see, just the 1, 0, 0, and 0. And we have 0, 0, 0, which is 0, and 0, 0, 0, 0, and last one, that will be 0 times 0 plus 0 times 0 plus 1 times 1, that will be 1. So when we have matrix A square, which is identity matrix, one of the identity matrices property, it will be any matrix times the identity matrix will be the itself. So when we have these two, we get the identity matrix 3 by 3, the identity matrix, which is 3, and then we combine another 2, that will be another identity matrix, and when identity matrix times identity matrix, it will be identity matrix as well. So as long as we have 2 pair of them, actually we don't need to be a pair, since we have to, because A have a negative 1 in the second row and the second column. So as long as 2 pair together, we get the final answer will be the identity matrix. So the answer of A to the 20th power, it will be identity matrix as well. Okay, let's move to question 35. If matrix C's A and B commute, show that A square B equals B A square. So in the normal case, the matrix A multiply matrix B is not always matrix B multiply matrix A, but it's not saying that cannot be the case. Just like the identity matrix, you can like commute, but the answer will be the same. So in that case, if they telling us A and B can commute, so we can say that will need us to prove this, and then A square B, which equals A times B, and if it commutes, so we can say we can move A and B, right? So we can like this, B times A, and then we can commute again. So we have, it doesn't change the value, so we have B times A and times A, and now at the end we associate those together, so which is B A square, which is indeed equals B times A square. That's it. Thank you.